I think you're muted.
Let's see, I'm muted. Can hear you.
Sorry about that. Hello, everyone. Welcome to this technical session brought to you by Hamuye. Hamuye is an EdTech startup with a mission to prepare young professionals and college graduates for their choice careers in data and the future of work. We do that via our internship programs, which simulate the conditions you will face while working in a real work environment. Our internships will expose you to specially designed courses, career coaching webinars with industry experts, and industry relevant projects, presentations like what we are having right now. My name is Mercy, and my job is to make sure you have a great experience at Hamuye. I'm joining you from Ibadan, Nigeria, and will be your host for today's session. I'd like to welcome you to this event. Everyone present, our incredible interns in the current cohort, kudos to you for making it this far. Thanks to the Hamuye Fellows and the Hamuye team who have made this session possible. For this session, we have Dr. Busola Sanusi. Busola Sanusi Akifaderi is a biostatistician with a PhD from the University of North Carolina, UNC. She is currently a lead biostatistician at the Johnson Research and Development Companies of Johnson & Johnson in the Oncology Early Development Group within Statistics and Decision Sciences. At UNC, Busola's methodological research focuses on non-parametric estimation of the joint distribution of survival time and mark variable, an endpoint indicator only observable at survival events in the presence of dependent censoring. Prior to that, she earned her undergraduate degree, summa cum laude, in mathematics and statistics from the University of Lagos, and a master's degree in mathematics from Central Michigan University. She was awarded the Vice Chancellor Prize for the best graduating students in the Faculty of Science at the University of Lagos. Busola was a fellow and a 3-year recipient of the Schlumberger Faculty for the Future Fellowship and was awarded the 2019 American Statistical Association Biopharmaceutical Section Award in recognition of her notable research, academic achievements, and applied project work related to the area of biopharmaceutical statistics. She has worked as a visiting research biostatistician at Merck Pharmaceuticals in 2016 and Takeda Oncology in 2017. She previously worked at the Harvard Center for Biostatistics in AIDS research and at the UNC Lineberger Comprehensive Cancer Center, where she focused on statistical study designs, data analysis, and made contributions to the advancement of infectious diseases research. We can see that our speaker for today has a very loaded CV, and she'll be sharing her thoughts and experience on the topic, Introduction to Survival Analysis, Application in Health Data Science using R. Before I hand over to Dr. Busola, please carefully take note of the following. Feel free to post your questions and comments on slido.com using the event code 3258972. I'll repeat this again, 3258972, and they will be promptly attended to. As you know, Busola will be taking us through 2 sessions. First, the technical session, and then the question and answer session. A Google form has just been opened to collect attendance for those present in this technical session. As we have told you that this session is something that would be recorded, attendance will be recorded. So you have to use the secret code, Hamuye, all lowercase, and the form link is being sent to all of the platforms right now. The form will be open for only 10 minutes starting now. The first attendance form link is now being pinned on YouTube and Zoom. We will want you to fill your form quickly in order to focus on the presentation. Thank you very much, everyone. And over to you, Busola.
Thank you so much, Mercy. I really appreciate the introduction. And I actually think some people are trying to get admitted into the meeting if there's someone monitoring as well. Okay. Okay, let me share my screen. I think I need to be made the host in order to share. I'm unable to share. Oh, okay, I can share now. Can you all see my screen?
Yes, we can.
Okay, thank you. So thanks once again for the introduction. And hello, everyone. It's a great pleasure to be here today to be given an opportunity to speak with you. I'm really excited to discuss this topic and also potentially plan a future interaction with you to explore more topics. As a start, I'd like to say this. I'd like to know how many of you actually have a statistics background? It doesn't necessarily have to be like a degree in statistics. It could just be like a course in school or maybe like an online course or even personal learning. So I'm hoping you'll be able to click on the thumbs up button here so I can just have an idea of how many people. So if you look at Zoom below, you would see the reactions and you can select the thumbs up button. Oh, interesting. We have, out of 68 people, we have 2. So that's really exciting because that means we have, I'll be able to, I've structured the slide in such a way that it is high level for those that don't have a background. So anyway, I have a brief background about myself. I know Messi already discussed this. So just briefly, I obtained my BSc in Mathematics and Statistics from the University of Lagos. And then I obtained my MA in Mathematics from Central Michigan University. And then in order to apply my technical background, I decided to explore biostatistics for my doctorate from the University of North Carolina in Chapel Hill. And for a few years, I worked at Harvard University as a research associate at the Center for Biostatistics and AIDS Research. And currently, I'm a research biostatistician at Johnson & Johnson Pharmaceutical Industry. And here is the fun stuff. I'm a wife and a mom of 2. So here are my 2 boys, and they keep me busier than all my research projects combined together. So that's that. So this is Eyumofe, and this is Fikayo. Okay, back to survival analysis. We'll start out with an overview. Then I'm going to discuss understanding time to event data. And then we would explore the concept of censoring. And then we'll delve into the definition of survival function. I'll briefly talk about methods for analyzing survival data, including the Kaplan-Meier estimator, the log rank test, the Cox proportional hazards model. And finally, we would explore the application in R. And I think there are 2 people in the waiting room. If there's someone that can please admit them in.
Yes, they're being admitted as you go. Don't worry about that.
Thank you. Okay. Thank you. Okay, so for the overview, I'll start with examples. Examples are always fun to start with from published articles. So here's an article from the Biomed Central Public Health Journal. In this article, they explored the risk factors associated with COVID-19 deaths in Mexican population using survival analysis. And this article was published in 2020. Okay. So I just display here 2 results from the article. Here in figure A, we see we have the survival probability on the y-axis and we have the time to event. I will touch more on this eventually, but just to introduce you to this concept, we have the time to the event, which is death due to COVID-19 on the x-axis. And then these colors represent the age group. So blue represents less than 25 years old, red represents 25 through 49 years old, green represents 50, and so on like that. And we can see that there is a direct relationship between the age and the risk of dying from COVID-19. So we see for those that are greater than 75 years old, you can see that their survival probability decreases over time. So they have a higher risk of dying from COVID-19 compared to the younger population. In figure B here, we have comparing the survival curves with regards to sex. So blue represents women and red represents men. Again, you can see that, I mean, this could be due to various factors, but here we're just seeing the results that the men have a higher risk of dying from COVID-19 compared to the women. So this is the first example. And here I have a second example. I have the source link here below. And this is also from an article. It's based on customer attrition. So customer attrition simply means loss of customers by a business. The question of interest here is, what's the probability of a customer discontinuing a subscription of a certain service? So from this figure, we see that subject A here completed the study up until the end, but we did not observe any. So this is the start of the study, the start of the subscription, and this is the end of the subscription. So by the end of this observation period, we did not observe anything about subject A. And I would introduce this concept later. This is called censoring. Then for subject B, they canceled their subscription during the study. Then customer C withdrew consent. So maybe you have a consent that you signed that you can share my personal data. You can always use my data to make analysis like this, but they withdrew consent. So there is a dropout. And then for subject D, again, like subject B, they canceled their subscription. So this is how you would observe a survival data. So for that customer attrition data, they collected a few features. So for example, each record in the data, by record, I mean observation in the data, has information about the customer's interaction. For example, the call history, the personal information, such as the age, their gender. They also collected their subscription information, such as the billing cycle, the product, the price. The data could also contain things like the call frequency. How many times did they call the company to complain about something? And as you would imagine, they also have information with regards to the duration of the subscription. So given all of this, we have these results from that article. And the graph shows that the time, it shows the time to customer loss prediction. So we have those customers that have monthly subscription, we have those that have annual subscription, and then just all combined. So you can see that those that have monthly subscription have a higher risk of canceling compared to those that have a yearly subscription, that's annual subscription. So this is another example. And you can also look at the individual level. So that's what's really cool about the survival analysis again. So we have 5 customers here. We have and if you look at all this, customer 2, which is red, has the highest risk of canceling their subscription, because you can see that the survival probability decreases over time compared to all the other customers. And one last example here, but I wouldn't go much in detail. I just wanted to also let you know, I recently published an article in collaboration with 2 other professors from the University of North Carolina. And it's just for you to see that survival analysis is applicable. This is with regards to the analysis of HIV vaccine research. You can apply it to so many areas. And again, I'll touch more on this soon. And here's our results from that article. So let's look at the overview. Survival analysis refers to statistical methods for analyzing the time until an event occurs. And as such, it is termed a time to event analysis. The time here that we are talking about refers to the duration from an exposure. So when I talk about an exposure, I'm talking about the start of your observation period up until the occurrence of an event that you're interested in. So say, for example, so we have the exposure onset all the way to your event. Okay, so for example, your exposure could be your disease diagnosis, COVID-19, and your events could be death. Another example could be treatment for, say, cancer, say, chemotherapy, and up until the patient relapses. Another example could be study entry. Say, for example, you have a population of heavy smokers that you recruited in your study for a prospective study. So you want to observe them for a potential event, which would be lung cancer. So this basically answers the question, what is the time until this event occurs? So now let's talk about the time to event in more detail. And here we'll be talking about time to event data. So time to event data means, as you would imagine, it's a type of data that measures the time taken for an event to actually happen. And your interest here is what is the time, like I said, what is the time until an event occurs. But what makes this also interesting is that you can even further answer the question, what is the probability of that event actually occurring, not just the time until that event occurs. And there are certain features of the time to event data. They include the time, and this time refers to the duration from your exposure to the event. Another feature is the event itself, which is the outcome of interest, what you're interested in. Another feature is censoring. So censoring means, like if you remember from the article that I shared, it means when an event of interest is not observed after the study period. So you have a certain period from the start to the end of the study, and then you don't observe events for certain subjects. It could be because you never observed the events by the end, or it could be because the subject withdrew consent. It could be because the subject died, was lost to follow-up due to different reasons. So we say such observation is censored. So on this slide, I listed a few areas where the time to event analysis is applied. The first, as you would imagine, clinical trials. So in clinical trials, you can determine how long it will take before a disease will reoccur. Say you treated someone from cancer and then they progressed, they did better, and then they regressed eventually. It could also be treatment failure or adverse responses in the sense that some medications have side effects. So time until you start experiencing side effects in the patient. So you can use this idea to actually determine if a treatment is efficacious or not. Closely related to this is in the area of general medical research, where the survival rate of the patient is explored, as we saw in the previous article, of the risk of COVID-19 in Mexicans. And definitely you can also use this in the time to event data is also present in engineering. And here you can use it to estimate the equipment failure, for the failure time for the purpose of maintenance needs, or just to optimize the performance. Definitely in finance, it is relevant to model or predict loan defaults for risk management. So there are certainly many areas where you can actually apply, you can see time to event data. And I'm hoping that this will just give you an idea in general. Now let's talk a little bit more about censoring. So as I previously mentioned, survival data are prone to censoring, and to reiterate, censoring occurs when you have unobserved events due to various reasons. So when there is censoring, we are usually faced with a missing data problem. And in these cases, when you don't factor censoring into your analysis, you would end up with biased results. So there are different kinds of censoring. The first is right censoring. So by right censoring, I mean a situation where the event has not yet occurred by the end of the study. There is also the left censoring. This occurs when the event of interest occurs before the start of the study. And then you have the interval censoring. This actually occurs when all you have is the information about the time interval that the event occurs, but you have absolutely no details about the actual time that the event occurs. So all these are cases that could happen, but the most common one is the right censoring, and this will be our focus for this discussion. And please let me know if I'm too fast. Okay, I'll try to slow down because I think I'm too fast. So this slide actually shows an illustration of how censoring could occur. Here we have 7 subjects. The blue represents your event of interest, whether a subject had an event or not. And then you have the censored, the black circle, whether a subject was censored. So at time 4 here, you see that subject 2 experiences the event of interest. And then subjects 4, 5, and 7 also observe the events during the course of the study. On the other hand, subjects 1 and 6 were censored. That is, they have no data after a certain point in the study before an event could be observed. Subject 3 here completed the study, but they had no event during the course of the study. So at the end of the day, we still say they are censored because we have no information. I mean, they could eventually have the event at time 12, but our study ended here. So there is no way for us to know, except there is an extended follow-up. But for this particular analysis where the time was defined for, say, 11.5 months, there is no way for us to know whether subject 3 actually experienced an event or not. Okay, So now we can gradually build on the concept of survival function. The survival function S of t, to briefly explain what this means, S of t simply means that this function S is dependent on the time factor. T here is your time. So S of t is a function of time. And the survival function represents the probability of surviving beyond a certain time. So you have S of t is the probability that your survival time is greater than a pre-specified time. So what's the probability of surviving beyond a certain pre-specified time t? Your survival function can be estimated using a parametric. By parametric, I mean that your data is assumed to follow a certain distribution, or it could also be estimated non-parametrically. In this case, there is less assumption, little to no assumption about the population distribution. So you really don't have to worry about this one now. The survival function is usually depicted as a curve, and this curve is called the survival curve. On the survival curve, what you have is the estimated probabilities over time. I'm going to show you soon, and we'll touch more on this as I proceed on the next slide. So the plot here is an example of the survival curve. So what we have are the survival probabilities on your y-axis. So you start out at 1. At the start of your event, everyone is there. So the survival is 100%, and then it could decrease over time. So your time is on the x-axis. So up until 50 days, you keep seeing a decrease in the survival time. The key components of the survival curve are the observed times. So what you have here is for all the participants you have in a study, you could either have an event or you could be censored. So one of these has to be observed for your participants. So your observed time is one of this. And next, what you have is event status. So this is just an indicator variable. What this means is whenever event time is less than your censoring time, you have 1, and if otherwise, you have 0. So this is your status variable. So consider this example where you have 10 subjects who were enrolled in a study. So you have subjects 1 through 10, and these are the time that they experienced an event. So for subjects 1, for patient 1, they experienced an event at time 2. For subjects at time 3, you have events for subjects 2 and 3. At times 5, you have 3 events for subjects 4, 5, and 6. At time 8, you have only 1 event. At time 10, you have 1 event as well for subject 8. At time 12, you have 2 events for subject 9 and 10. Okay, so here remember S of t represents the survival function. What's the probability of surviving beyond time t? At time t equal to 0, you don't have any events. Everyone is in the study. So your survival probability is 1, right? At time 2, on the other hand, there is 1 event, patient 1. So what this means is that the probability of having an event, if you remember, if you have a background in probability, so if you have 1 event and then you have your risk set, which is the number you're considering, population set, the probability of failure, if it's just 1 event, is 1 divided by your n, which is your total in your population. So the probability of having an event is 1/10. But what you're interested in is the probability of surviving, not of failing. So it's going to be 1 minus 1/10, which is going to be 9/10. At time 3, you have 2 events, but you already had an event at time 2. So this makes a total of 3 events by time 3. And the probability of failing or having an event at time 3 will be 3/10. So the probability of surviving will be 1 minus 3/10, which is 7/10. And this goes on up until when you have your survival probability being 0. So we can display this on the curve for more clarity. And I've copied the survival functions, the estimates here on the left side. So we see that the survival, I have an aggregate here. Remember on the previous slide, what we have is just the count of events at each time point. But now you can see that at time 2, so you had 10 people at risk at baseline, there was no events. At time 2, you still had 10 people at risk initially, but then you have 1 event. At time 3, because you had 1 event, you now have 9 people, only 9 people left at risk, but you have 2 events at time 3. Now that you have 2 events and 3 in total, you know that at time 5, your risk set will be 7, and then you had 3 events and so on. Okay. So we see that the survival probability corresponding to 2, like we previously said, is 0.9, and the survival probability on this curve, and the survival probability corresponding to time 5 is 0.4. So this curve gives you a quick and better representation of your estimates. You don't necessarily, sometimes in data, you may have like tons, maybe even 200 data points. You don't want to see all this, but when you have a curve, you can have a clear idea of how the data is, the summary of the data. And notice here that we haven't said anything about censoring. So this is just assuming that you have no censored data at this point. On the other hand, you can have an example where you have censored observations. So here we have 1 event again at time 2. At time 3, we have 1 event, but then I switch this to censored. So you have 1 event and 1 censored. At time 5, you have 3 events. Time 8, you have 1. Time 10, you have 1 event. And time 12, you have 1 censored and 1 event. Again, the second table shows the aggregated summary. So N represents, again, the risk set, D represents your events, and now we have this extra row, which represents your censored. So at time 0, you have 10 at risk, no events, no censored. At time 2, 10, 1 event, no censored. At time 3, now you have only 9 at risk, 1 event and 1 censored, and so on, if that makes sense. I'll just give about a few seconds to understand what's going on here. Okay. So yes, so here basically what we have is the survival probabilities, and you can see that there is a difference compared to what we had when we had no censoring. So we see that at time 0, your survival probability is still 1, but instead of just stopping at 9/10 at time 2, we now have to factor in censored. The formula to calculate this is by multiplying your current probability of surviving by the previous. So your survival probability at this time, and you had survived this period of time, if that makes sense. And that will be a multiplication of these two, and that will be 0.9. Similarly, the survival probability at this time. So remember here, your risk set is 9, n equals 9, and then you have 1 event. The probability of having an event at time 3 is 1/9, but your interest is the survival. So the probability of surviving at time 3 is 1 minus 1/9, which is 8/9, and this is what we have here. Then multiplied by your previous probability, which is 0.8. And then this goes on up until time 12. So for example, time 10, time 12, you have 1 event, and your risk set is 2. So the probability of failing, the probability of having an event is a half, right? That means the probability of surviving is also a half. So you'll be having 0.5 multiplied by 0.2, so 9, if that makes sense. And then you have this curve as well, the corresponding curve. And again, I'll give a few seconds for us to observe that. Okay. And again, please let me know if I'm too fast. So let us briefly discuss the log rank test and the Cox proportional hazard model before we then go into the application in R. So log rank test is a survival analysis method. It's used to make comparison between 2 survival distributions, 2 independent groups. So you could have, so for example, you have this black survival curve and you have this brown curve survival curve. And you can observe that the group in black have a lower survival rate, or you could say a higher risk of having an event compared to the group with this brown survival curve, if that makes sense, because you can see that the survival probability decreases over time for this group in black compared to this group in brown. Okay. So this is a little background about the log-rank test. The aim is to examine, it's a test to examine whether or not there is a difference in the survival distribution between the groups that are being tested. And this is what we call our underlying or our null hypothesis. So your null hypothesis is there is no difference in the survival distribution between the groups. And then your alternative hypothesis, more like the opposite, is that there is a difference between the two groups. So how do you decide? Your decision rule is based on whether or not your p-value. So your p-value is a metric for either rejecting or failing to reject an hypothesis, whether or not that p-value is greater than your significance level. In this case, we have 0.05. We'll not spend a lot of time on this, but the whole idea is that you want to make a decision depending on whether your p-value from your analysis is less than your significance level. So it's a measure that helps to determine whether determine the strength of evidence against a certain null hypothesis. So if your p-value is less than 0.05, we would fail to reject the null hypothesis. And if it's less than, you would reject, and if it's otherwise, you would fail to reject the null hypothesis. We do not say accept. So that's a caution here. In statistics, we don't say, or data science, we don't say accept, we say fail to reject, because then it means you just need more information. But if it's less than 0.05, you know certainly that you would reject your null hypothesis. So on this slide, I just provided the formula for computing the log-rank test statistics. By test statistic, what I mean is a value that you obtain from your data to assess whether your data provides evidence for or against your null hypothesis. So you can see the relationship between this and your p-value. They work hand in hand. So again, it is that value that you obtain from your data to assess whether your data provides evidence for or against your specific hypothesis. So O sub A here represents your observed value in group A. O sub B represents your observed values in group B. E sub A here represents your expected value in group A, and E sub B represents your expected value in group B. And your O sub A is just the sum of events in group A. Your E sub A is computed in this way. So you have your events in sum of events in group A and B. Then your risk set, remember, N represents the risk set. So you have the total population, sorry about that, the total population in group A and B, then multiplied by, since this corresponds to A, you multiply by the risk set in group A. And this log-rank test statistic follows a chi-square distribution with 1 degree of freedom. So again, I'm not going to go in detail in the technical detail, but the whole idea is once you obtain your log-rank test statistic, your LR, and you know it follows a chi-square distribution, we have the chi-square table, which you can look up to then correspond that to the p-value. And once you get your p-value, then you can then make your decision whether or not to reject or fail to reject your null hypothesis, if that makes sense. I mean, we are just introducing the background here, but the whole idea of this is for us to know that we can actually automate the process using R. So even though this is actually very, very important for you to know, but you also need to be able to eventually automate this without having to do all of this manually. So consider this example here. Your status is your event. It's 1 if you have an event, and it's 0 if the subject is censored. So we have the time to event data for groups, for these two groups for comparison, group A and group B. This is the time for group A, and then we have whether or not they have an event. So for example, in group A, we have 1 event at time 2, we have 1 event and 1 censored observation at time 3, and so on. And then in group B, we also have the times that we observed events or maybe a censored observation. But in this case, we only have events for group B. So again, we have the aggregated table. So this is similar to what we had before. So for example, in your group A, there are 8 subjects that are at risk at time 2, and then you have 1 event. So now we have the subscript just to specify whether it's group A or group B. You have 1 event, and then you have 1 censored. You have non-censored in group A. And then at time 3, you have 1 event and 1 censored, and so on. But one thing that makes this different from the other is that you would make sure that you would accommodate all the times for time A and B. So this time accommodates all the times that are present here. For example, time 6 is not present in group A, but because you're making comparison at each time point, you'll be having time 6 here for this aggregated data, but only that you'll be specifying that for group A, you had no events and you had no censored observation, if that makes sense. So using the formula that I previously provided for the log rank test, you can obtain your your expected values for group A and group B as follows. And then if you use the formula, you would be able to obtain, your observed value, and then your expected value, you sum across and you get 0.04. And remember, we mentioned that this follows a chi-square distribution. So you can always look up the chi-square table to correspond this to the p-value. And the p-value here is 0.95, which is greater than 0.05. So we would fail to reject the null hypothesis. That is the null hypothesis that says that there is no difference in the survival distribution between the 2 groups. Again, if I'm too fast, please let me know. Okay. So briefly, we'll talk about the Cox proportional hazard model. So one very good advantage of the survival analysis is that we are able to not just determine the time until an event occurs, determine the probability of an event occurring. We can also explore if there is a relationship between some features and your survival probability estimates. And the Cox proportional hazards model is the best candidate. It's a regression model to address this. So very briefly, it's a regression model that examines the effect of variables on the survival time. And these variables, or I know in data science, sometimes we call them features, they are factors that may be associated with the survival time. So therefore, it is very crucial for us to be able to determine if they actually have an impact on our estimate. So for example, we see here the survival curves for 2 groups, the survival distribution for 2 groups, for the group less than 30 years old in brown and the group greater than or equal to 30 years old in black. And we can see that being at least 30 years, so being 30 years or older, is associated with a decreased survival. Yes, it's the black one, yes, being greater than or equal is associated with a decreased survival compared to those that are younger than 30 years old, because you can see that the survival estimate here decreases at a faster rate compared to those that are less than 30 years old. Okay, now to the fun part. We would discuss the application in R. So the R programming is the R programming language is a free open source application for automating statistical or data science methods, and it has a vast applicability in data science. So for you to install R, you would go to r-projects.org, this website, and once you're on the web page, this comes out. You would click on download R. It's pretty easy to follow once you just go to those. Even if you just Google install R, you would get to this link. And once you click on this download R here, where my cursor is, it will take you to this page where you can actually select a location that is closest to you, but it's easier for you to just click on this very first cloud, because this would automatically take you to the most efficient, the closest location to where you are. Okay. So when you click on the cloud, you will get to the R archives, this page, and here you'll be able to choose your operating system. So for example, if you use a Mac OS, then you can click this. If you use Windows, you can click this. If you use Linux, and so on. And it will take you to a final page where you can then download the most recent version of R. So I'm going to switch to R now. So this is what your R environment looks like when you first open. So you have where you actually write your code, you have your console. So whenever you run a code here, it comes here. This is where you have, for example, some summaries, tables, and you could also have like errors that will be prompted here. You have this environment here, which shows you your data, your global environment. It should show you your history as well. And then I would show you examples. And then you would also have this last environment on the bottom right, which will show your packages, your plots, and so on. And you can always export your results in PDF or whichever HTML. So first things first, R is case sensitive. So for example, if I had written survival this way, this is not going to run correctly. So we have to keep that in mind. R is case sensitive. We start out by installing the packages. So each
Sorry to cut you short, Busola. I think we can see your
oh, you can't?
application.
Oh no.
Yeah, we can only see your slide. Yeah.
Oh no, I'm sorry.
Okay.
Let me reshare. Let's do this. How about now?
It's coming up. Can't see it yet.
You can see?
Yeah, we can see now.
Oh, okay. I'm so sorry. So again, this is the R environment. You would have these 4 different environments. You have here your code. You have here below the bottom left where you would have, whenever you run a code, it pops here. You have summaries that will be displayed here. And errors, if you have errors in your code, it would also display here. On this top right, you would have things like your data sets. You could also have history. And on the bottom right, you would have your packages that you can install. You can have help. You can always export to say PDF or HTML. Then you have your plots that would also be displayed here. And you can always tweak this to what suits you best. Like, for example, sometimes I prefer this console to be fully here so that I can really see my results fully. But it all depends on the user preference. So like I said, R is case sensitive. And the first thing you do here is R has some inbuilt packages. So for example, we are discussing survival analysis. So here we have the library survival. What you want to do first, and you don't have to actually remember all of these packages. R is really, really effective when it comes to this. It's a really good programming language. If, for example, I just started running all of this, R is going to tell me that, oh, there is an error. You need to install this survival package, for example. So then I would come here and search. I'll click on install, and then I'll search for survival. And once I click, you can see that this just pops up, and then you click on install, and then it's going to install the package for you. So you don't need to remember all this. And once you install this package, it just says that it is present. But then for every session of your program, you actually, I know that there is an updated version of R that if I don't have all of this here, it's also going to tell you that, oh, you need to load your package. So I want this package to actually be available for me in this session. In order to do that, you would have to run this. So give me the library survival. This is just for data wrangling. I also want this, which is associated with survival. So after loading these packages, these are now present in this environment, this current working session. If you close R and you come back and you want to run survival analysis, you always have to load those packages. Okay, so the next thing you want to do is you want to read your data. For example, you could have your data, say, in a path on your computer. So this is my data path, and then you could just read your Excel. It could be a SAS data, text data. You can always read it. And another thing that is really, really cool about R is that they actually have inbuilt data. So if you just want to learn programming, if you just want to learn application in R, you don't necessarily have to have data on your computer. All you need to do is load. So here sorry to let you know. Yeah, I'm sorry about that. You can always highlight to run. You can always highlight, and then or you could just click on the line you want to run. Then you click on Control Enter, on your Mac, it's going to be Command Enter, and that would just run that line for you. So that's really cool. So that's how I'm running all this. Windows Control Enter, on Mac it's Command Enter, and then it's going to show you what you just ran below here. So you may be interested in seeing like the first few observations in your data set. So that's what this line does. You have your head long. So it's telling me, give me the head of your data set. And I'm going to expand this so that you can actually see. So we have your time to events, you have your status, you have your age variable, you have your sex variable, and so on, and all of that variables, all of that features in your data set. You may also be interested in knowing how many people actually have an event or how many people were censored. In order to do that, you can tabulate. So that's what this table function does. And then if I just Control Enter, I can see I hope you can all see. I can see that 1, we have 63, and then for 2, we have 165. Now for in survival analysis, the traditional method is usually to have 0 or 1. So 1 will represent censored events, and events and censored events will be represented by 0. So in order to do that, we want to actually reformat our status. So currently our censored event is represented by 1 in the data, and we have 63 censored events. And then our events variable is represented as 2. So we have 165 events in our data. So what we actually want to do is we want to be able to, so I'm saying that modify my data, mutate my data such that you can now recode 1 as 0 and recode 2 as 1. So once I run this part of the code again, you can see that it's popping up here. You can see, remember I said that this environment can show your data, so you can always just view your data, the information about your data here. Now I'm going to view, because it's always good to check if your code is running properly. So I'm going to again Control Enter, head long, just to see if my data is now how I want it to be. So you can see that your status is now 0 and 1 from 2 and 1, if that makes sense. And again, you can just tabulate to see clearly that now censored is 0 and your event is 1. Another really nice thing about this is that you can always do descriptive statistics. There's so many possibilities, and it's so nice because when you think about summary, it's not really complex to think about. It's summarizing your data. So that's really nice about R. It's like a user, like a regular human language. So I want to see a summary of my time. And it just gives me the summary. It gives me the minimum, the maximum, whichever. Sometimes these are like the standard, but you can always specify what you want. I also want to tabulate my sex. I want to know how many men or how many women are in my data set. So those are summaries. Okay. Now that we have our data in the form that we want, we can now create our survival curves. So in order to do that, we want to use what is called the sort fit function. And there is an R documentation. Again, you don't have to remember all this. This is just introduced to survival analysis. You can apply this to any other projects that you're working on. But for this particular one, you can always check the R documentation as well. So the sort fit function, I'm going to create. So I'm saying that create KM solve. This is a user-defined variable. So I'm saying save my survival data, whatever I want to do, this summary, in this newly created variable KM solve. And I want to see the structure of what I just created. So you can see again str. That reminds me that I want to see the structure. So str of KM solve. Once I click on this, it gives me this summary of exactly, and remember we're talking about the risk set. You don't have to do this manually. This is so cool because now you can see the summary being provided here for you. You can see the number of events at each time. You have the time, and then you have the number censored at each of this time as well, and so on. So in order to see the summary of my objects that I just created, as KM solve, I'll just click on this. So this gives me a more detailed summary for each time points in the data set. So you can remember I was saying that if you have just 5 data points, it's okay to just like manually compute. But see how much data points we have. You don't want to do that manually. So this actually computes that for you. And at each time point, you can actually see the number of events, the number at risk, and the survival probability. So at time 1, your survival probability is 0.9956. And this goes on up until the last in the data set, the last time point. Okay, and then you can plot your survival curve. So again, I just did Control Enter. On your Mac, it's going to be Command Enter. And once you plot your survival curve, I can expand this to say clearly, you have your survival probability on the y-axis, and then you have your time on the x-axis. I am interested in also seeing my number at risk below this curve. So all I need to do is I'm asking R using the GG subplot. So this is an R function. I'm asking R, provide the risk table for me. I don't want to be having to look at all this. I just want a summary here. And you can just do that. And once you do that, R provides this summary table for you. And you can see the number at risk at time 0 is 228, and so on, if that makes sense. So another thing that you may actually be interested in is what's the probability of surviving up until a certain time. So again, you see how nice this is. You can actually determine, oh, at time 500, what's the probability of surviving? I don't need to strain my eye to actually try to trace this out. All I need to do is I tell R, give me a summary. So I don't know if I mentioned this, in your soffit, you have your time variable and your status. I must have skipped that. So you know, you have the time factor, you specify your status, whether it's an event or a censored observation. And what 1 here means is that, oh, I'm not looking at any other covariates or any other variable or feature in my data. Just give me the summary based on the time and the status. And my data is the log data. Okay, and here I'm interested in the time. So the survival probability to up until 500 days. Once I click on the summary, it tells me that by 500 days, my survival probability is 0.293. And I have 41 people at risk. I have 138 people that have an event as at that time. And you see that this corresponds to what we have here in this curve. So that's really nice. I would like to show you, I'll go back to my slides and I'll show you, and this is exactly what I'm showing you now in R. I just thought it would be nicer to show you how to run it. But I wanted to let you know, yeah. So if you had ignored censoring, remember we had that our number at risk is 41 here. Let's see the number censored at this time point 500. You can always compute that here as well. So I'm going to compute that. Tell me the summary. So I have 49 people that are censored. Assuming you didn't factor for censoring, then what you would assume is, oh, I have 49 plus 41, which is 90 events by time 500, which would be incorrect. So if you had not considered censoring, you would be saying that there are 90 events at this time point. So this is your probability of having an event, and then the probability of surviving. So 500 days would be 1 minus that, which would be the percentage is 60.5%. And that would have been wrong because what we actually got here was 0.293. I hope that makes sense. Okay. So the next thing is that we can also check if there is a relationship between sex and the survival estimates. So, for example, you may be interested in knowing whether your sex will determine whether this, if there is a difference in the survival distribution based on the sex. So I'm again going to run similar to what we had before, but if you notice now we don't have one anymore. What we have is sex. So I'm saying group this by sex. And then I can also get the summary. I'll just click on the points that I want, Control Enter, and this will give me the estimates by sex group. You can see sex equals 2, and above you would have sex equals 1. So these are the survival estimates for each sex group. Then I can plot and tell R, provide the risk table as well for me. So you can see that for sex 1, depending on whether it could be the male or female. Let's say male is red and female is cyan. So you know that for this cyan color, the risk of the probability of surviving is higher compared to this red group. So the risk of dying is higher. If it's death, we are considering the risk of dying is higher in men compared to women. And I hope this gives you a whole idea, a little background of how cool R is. And again, I'm very happy to always help. I have my LinkedIn, I have my Gmail. You can always reach out to me for more if you need. So in summary, survival analysis, which I said is also known as the time to event analysis, is actually a branch of data science that focuses on analyzing the time until an event of interest actually occurs. We explored two methods. We explored the actually three: the Kaplan-Meier estimator, we did the log-rank test, and then the Cox proportional hazards model. So the Kaplan-Meier estimator, we use this to estimate the survival function. And remember, we said it's the probability of an event occurring or not occurring. You can use that for both until a specific time point. You can use your figures to compare survival curves like we did between two different groups or categories. And then we looked at our Cox proportional hazard model, where you can actually assess the relationship between the covariates and the risk of an event occurring. So for this Cox proportional hazards model, I'll just quickly go back to R. I want to show you how nice that is. So if I actually want to see, all I'm saying here is that these groups differ. I want to see if they actually differ significantly. Do we want to be computing this and then going to chi-square table? You don't have to do that. You can always just run this sub this function. So this is exactly what the log-rank test is we discussed before. So you have your expected, remember this formula? You have this formula, you have your observed value and your expected value. And now we have this p-value. And it's saying that the chi-square statistics, your log-rank test statistics is 10.3 with 1 degree of freedom. And your p-value here is 0.01. So you know that you would reject your null hypothesis that indeed the groups actually differ significantly. Okay, so we go back to the slides, and you can also definitely use survival analysis in machine learning. It can be used to model and predict the time to event outcome based on various features or covariates, as we call in statistics. Different methods exist here. You have the random survival forest. This actually involves feature selection, prediction, and training multiple survival trees on different subsamples of the data set, and which is often done with replacement. The predictions from these trees are then averaged to obtain something that is more robust and reliable. There's also the deep learning models, which such as the recurrent neural networks and long short-term memory networks, and they can also be applied to survival analysis. So these methods actually capture complex temporal patterns and dependencies in the time to event data. And then finally, you have your gradient boosting survival analysis. So this basically involves building an ensemble of weak survival models in a sequential manner. So each model is trained to correct the mistakes or residuals made by the previous models, and then you can improve the accuracy in your prediction. So these are other examples that you can actually use in machine learning. So we said that survival analysis involves a learning framework and a set of techniques that are utilized for estimating the duration of the time required for a specific event to occur based on your observed data. And we can actually combine the framework of survival analysis as well as the predictive capabilities of machine learning for significant business value, and it can be applied to various applications, like we said, in predictive modeling, in patient monitoring. We talked about finance, we talked about marketing analytics, and then engineering and economics, and so much more. And thank you so much. I have my J&J email, I have my Gmail. You can always look me up as well on LinkedIn, send me, connect with me. I'm so happy. I know I went through the entire 1 hour, so we may not be able to answer all the questions today, but feel free to reach out to me. It's clearly my Gmail, busola@gmail.com. That's easy to remember, and I would be more than happy to connect with you and discuss more. Thank you so much.
Thank you very much, Dr. Busola, for that very informative, insightful session. I've actually learned a lot listening to you. We appreciate your efforts in explaining all of those concepts. Thank you. So just before our speaker takes some of your questions, please note that the second attendance form will be dropping now. And the secret code is Python, all lowercase. I repeat, Python. So the form will be dropping on all platforms now. Remember that the form will close 10 minutes from now. Check YouTube and Zoom for the new form, please. And now to our questions. We don't actually have like a lot of them. Remember to post your questions and comments on slido.com using the event code 3258972, and they will be promptly attended to. So let me just take the few ones that we have. From Oladimeji Williams, we have, because life is irredeemable once lost, what is the best metric for evaluating classification models on medical data? I don't know if you got that.
Yes, I didn't get the first part, but I heard the parts where the best method for analyzing medical data. But because life is, I didn't get the first part.
Yeah, he said, because life is irredeemable once lost, what is the best metric for evaluating classification models on medical data?
Yes, when we talk about medical data, mostly we use, but it depends on the situation as well. So if you have, for example, like I said, covariate dependencies, so you have covariance that of variables features that are actually predictive of your model, then you want to look at the Cox regression model. And most of these methods work hand in hand. In terms of the most optimized method, it's really relative. When it comes to medical data, we use Cox regression model or the Kaplan-Meier estimator because it relies less on distribution. It factors in censoring, like we discussed as well. And I know that there are also machine learning methods that we discussed in the summary. So maybe the question came in earlier that we discussed in the summary that would also be applicable and equally as optimal as the Kaplan-Meier or the Cox regression model. But generally in medical line, we use the Cox regression where there are covariance dependency. You can use the Kaplan-Meier, and then you have a log-rank test as well.
Thank you very much. Okay, we also have p-value tests better than chi-squared when selecting important features. Is there any better method for determining important features? I don't really understand it, but like that's exactly how it is written here, and I guess that's how the person
yeah, that's a good question. Maybe if I'm going to rephrase it to how I'd ask, maybe I'm not sure if that's how you probably what you have in mind, but the best way to actually know, that's a very good question. We didn't touch on that. So all I just gave was example that let's say age or sex is predictive of your outcome, say death, right? So normally we also have the generalized linear model, for example. You could also have your logistic regression model. So those are further down the line. I'm talking about statistical methods that you can actually determine whether or not your variable, your feature is actually really predictive. So we just don't guess that, oh, sex is predictive of your outcome. We actually test which of those features are actually predictive. So when you have, like, for example, binary outcomes, you yes or no outcome, we tend to use the logistic regression model. And then when you have continuous outcomes, say you have, by continuous, I just mean regular numbers on the number line, negative infinity to infinity, we can use the generalized linear model and several other models to actually check whether your covariance is predictive. And then when you obtain the variables that are actually, or features that are actually predictive of your outcome, you can then impute them in your survival model to get your estimates, your survival probabilities. So that's a very good question.
Thank you very much. I think that was well answered, actually. Is there any relationship between the first and second table during your presentation slide? I think this was asked while you are presenting.
That's a very good question. The first table is actually the data as is. I'm looking for where I have that. Okay, this is just the data as is, showing you a summary of all the subjects in your data, and then you have your time points as well. This is your aggregated table. So it just shows you the summary. So instead of having time three here, all you're saying is the unique time points. So it's pretty much the same thing, but all you have here are the unique time points in this data. And then you can say that for this unique time point 5, you have 3 events. So it's pretty much the same thing, but this is just an aggregated version of your original data. And this is what your survival table is estimated to be created from the second table, the aggregated data. So yeah, that's a very good question.
All right. Thank you. We also have here, I think there is a bit of confusion at ST equals to 5. Maybe the person was kind of confused as to how you got one of the values. So the question just says, I think there's a bit of confusion at ST equals to 5.
So here, I'm guessing it could be this one. I'm not sure, but let's say it's this one, for example. Here, we don't have censoring being considered. So what you have is, if you have, let me give an example. So if you have 10 students in a room, the probability of selecting 1 student out of that room is 1 out of 10. So 1 over 10. If you have 3 events out of 7, the probability of, without considering censoring, the risk set is always 10. The probability of having an event is 3 out of 10. But what? Okay, I see. Thank you. That's a good point. So yes. So you have 3 events out of 7. So what you would have left is 1 minus 3 over. Oh yes, I have a typo. It should be 6. Thanks for the catch. Yes.
Okay.
I have a typo.
Thank you. All right. Thank you for explaining that. Can survival analysis methods, this is the last one. Can survival analysis methods undo high-dimensional data of different data modalities used in cancer research?
Yes. So
should I come again? Okay.
That's good. Thank you. So that's actually where machine learning comes in. For example, in research and development, where I work at Johnson & Johnson, we have I work in early development, but those that work in late, so early development, we are still trying to determine whether the drugs are safe. Then we have late development, where the safe drug is now being tested in a larger population. So in that, we have high dimensional data, and we have people that work in modeling machine learning in that area in Johnson & Johnson. So in a case like that, you would definitely employ machine learning methods, because that's where the basic survival methods may fail, because they may not be as efficient as the machine learning methods. And those are some of the methods I listed at the end of my slides.
All right. Actually, as you were speaking, one person asked another one. So I think we should just pick that one and round up. What are some common challenges or limitations when applying survival analysis techniques to healthcare data? And how can these challenges be addressed?
Yes, so we keep improving. So the paper that I shared with you that I published earlier this year, it covers situations like that. So one of the limitations is this here. So it's a non-parametric estimation of max survival data in the presence of dependent censoring. So you could actually have, it's not just about having censoring that, okay, you have patients that are lost to follow-up, or patients that did not complete or withdrew consent. You could also have variables in your data, like someone asked in one of the questions, that are actually predictive. So they are not just censored, but the probability of censoring affects your outcome. The probability of censoring, the variables that correspond to those that are actually censored matter, plainly put. So in a case like that, you also want to involve, there's something called the inverse probability censoring technique, which I used in this paper. So that actually addresses cases like dependent censoring. So there are always challenges that come up like that in survival analysis, and we keep building more methods to actually address those challenges. I don't know if that makes sense, if that's clear.
No, that makes a lot of sense.
Okay.
Thank you very much, Dr. Busola, once again. We've officially come to the end of today's webinar. I want to thank Dr. Busola for taking the time to educate us today. Every second has been totally worth it. I also want to thank you, our dear interns and visitors, for joining us today. I'm certain you've gained some valuable insights and knowledge. A big thank you as well to the Amoye team and everyone who saw to the success of this webinar. Until next time, have a lovely weekend.
Thank you. Thank you, everyone.
Thank you, Dr. Busola.